Our universe is vast. It's filled with billions of galaxies, each teeming with stars and planets. But it wasn't always this way. Scientists believed that the universe began from an incredibly small, hot, and dense state. Then, in a fraction of a second, it expanded exponentially. This period of rapid expansion is known as cosmic inflation. Imagine something smaller than an atom exploding outward. In a tiny fraction of a second, it becomes larger than our solar system. That's the power of inflation. It's a mind-boggling concept, but it helps explain many of the things we observe about the universe today. But what caused this incredible expansion? The answer, physicists believe, lies in a mysterious field called the inflaton field. This field is thought to have been responsible for the rapid expansion of the universe. The inflaton field caused energy to spread out, leading to the creation of space and time as we know it. As the universe expanded, it cooled down, allowing particles to form. These particles eventually combined to form atoms, the building blocks of matter. Over billions of years, these atoms came together to form stars and galaxies, and that's how we ended up with the vast, complex universe we see today. From a tiny point to a universe filled with wonders, the journey of our cosmos is truly awe-inspiring. The inflaton field is a hypothetical field that existed in the very early universe. Like a ball rolling down a hill, the inflaton field released its potential energy, causing the fabric of space itself to stretch and expand at an incredible rate. Think of it like blowing up a balloon. As you blow air into it, the rubber stretches and the balloon expands. The inflaton field acted like the air, and the fabric of space was the rubber of the balloon. This rapid expansion driven by the inflaton field is what we call inflation. It's a crucial part of our understanding of the early universe and helps to explain some of the most fundamental properties of the cosmos. Before the theory of inflation was proposed, cosmologists faced significant challenges in explaining certain fundamental aspects of the universe. These challenges were not just minor details but rather profound mysteries that questioned our understanding of the cosmos. Two of the most perplexing mysteries that cosmologists grappled with were the flatness problem and the horizon problem. These issues were so significant that they demanded a revolutionary explanation. The flatness problem refers to the observation that the universe appears remarkably flat when viewed on large scales. This flatness is not just a trivial detail, it has profound implications for the overall geometry and fate of the universe. This observation is puzzling because, according to classical physics, any slight curvature present in the early universe should have been amplified over time. This amplification would lead to a universe that is either highly curved or closed, which is not what we observe today. The horizon problem, on the other hand, deals with the remarkable uniformity of the universe. This uniformity is seen in the cosmic microwave background radiation, which shows that regions of space separated by vast distances have nearly the same temperature. This is perplexing because these distant regions should not have had enough time to interact or exchange heat, given the finite speed of light and the age of the universe. How could such distant regions be so similar in temperature? The theory of inflation provides elegant solutions to both of these problems. It suggests that a rapid expansion of the universe occurred just fractions of a second after the Big Bang, stretching the fabric of space-time. This rapid expansion would have smoothed out any initial curvature, much like flattening a crumpled piece of paper. This explains why the universe appears so flat today. Furthermore, inflation proposes that the universe was once incredibly small, allowing regions that are now far apart to have been in close contact in the past. This close contact would have allowed them to reach a uniform temperature before being stretched apart by inflation. By addressing these two major problems, the theory of inflation has not only deepened our understanding of the early universe but also provided a more coherent picture of its evolution. It stands as a testament to the power of scientific inquiry and the human quest to unravel the mysteries of the cosmos. Believe it or not, quantum mechanics, the science of the very small, played a crucial role in shaping the large-scale structure of the universe. During inflation, tiny quantum fluctuations, which are inherent to the nature of space and time, were stretched to enormous sizes. Imagine a tiny ripple on the surface of a pond being stretched out to become a giant wave. These stretched quantum fluctuations became the seeds for the formation of galaxies and other large-scale structures in the universe. Without these quantum fluctuations, the universe would be a very different place. it would be smooth and uniform, lacking the rich tapestry of stars, galaxies, and planets that we observe today. Section 5. Echoes of creation, the cosmic microwave background. If inflation did occur, we should be able to find evidence of it. And indeed we have. The cosmic microwave background, or CMB, is one of the most compelling pieces of evidence supporting the theory of inflation. This faint afterglow of the Big Bang is a bath of radiation that permeates the entire universe, providing us with a snapshot of the early cosmos. The CMB is not just a random glow, it contains subtle temperature variations that are incredibly significant. These variations reflect the quantum fluctuations that were present during the period of inflation, moments after the Big Bang. Scientists have meticulously mapped these variations, revealing a detailed picture of the early universe. This radiation was emitted about 380,000 years after the Big Bang, a time when the universe had cooled enough for atoms to form. Before this period, the universe was a hot, dense plasma where light couldn't travel freely. As the universe expanded and cooled, it reached a point where protons and electrons combined to form neutral hydrogen atoms, allowing light to finally travel through space. This moment, known as recombination, marks the release of the CMB radiation we observe today. The CMB provides a wealth of information about the early universe, including the density and composition of matter, the rate of expansion, and the nature of the initial fluctuations that would eventually grow into galaxies and clusters of galaxies. The temperature variations in the CMB are incredibly tiny, just a few millionths of a degree, but they are crucial. They provide a direct link to the quantum fluctuations that occurred during inflation. These fluctuations were stretched to cosmic scales, seeding the large-scale structure of the universe we see today. These variations provide a snapshot of the very early universe, a time when the seeds of galaxies were just beginning to sprout. By studying the CMB, scientists can trace the evolution of the universe from its earliest moments to the complex structure we observe today, offering profound insights into the nature of our cosmos. Section 6. Planck and WMAP, peering into the infant universe. Scientists have developed sophisticated instruments to study the cosmic microwave background in detail. Two of the most important missions are the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck satellite. These missions have provided the most precise measurements of the cosmic microwave background to date, revealing the temperature variations with incredible accuracy. The data from these missions strongly support the inflationary model and have helped to constrain the properties of the inflaton field. Imagine looking at a baby picture of the universe. That's what the cosmic microwave background allows us to do. And the data from WMAP and Planck have given us the clearest picture yet. Section 7. Beyond the horizon, challenges and alternatives. While inflation is a compelling theory, it's not without its challenges. Some physicists argue that the inflaton field is too ad hoc, meaning it lacks independent evidence. Others point out that inflation doesn't explain everything, such as the nature of dark matter and dark energy, which make up the vast majority of the universe's energy content. Alternative theories to inflation have been proposed, such as the cyclic model, which suggests that the universe undergoes cycles of expansion and contraction. Section 8. The quest continues, unraveling the secrets of inflation. The quest to understand the very early universe is far from over. Scientists are constantly searching for new ways to test inflation and to explore alternative theories. Future telescopes and experiments will provide even more precise measurements of the cosmic microwave background, allowing us to probe the inflationary epoch in greater detail. Researchers are also developing new theoretical models to better understand the inflaton field and its properties. The study of cosmic inflation is a journey into the unknown, a quest to unravel the deepest mysteries of our cosmic origins. Section 9. The elegance of the universe, a final thought. The theory of cosmic inflation is a testament to the power of human ingenuity. From a simple set of ideas, we've been able to construct a model that explains many of the fundamental properties of the universe. While there is still much that we don't know, the elegance and explanatory power of inflation are truly remarkable. It's a reminder that the universe is full of surprises, and that the pursuit of knowledge is a journey without end. The universe began with a bang, and we're still feeling the reverberations today.